Welcome to Advanced Learning Tutoring. This is the Physics playlist. Please like this video and subscribe to our channel. Forces and motion, distance and displacement. Distance is a scalar quantity. It is how far an object moves. Distance does not involve direction. Displacement includes both the distance an object moves, measured in a straight line from the start point to the finish point, and the direction of the straight line. Displacement is a vector quantity. An example is a running track. If you run a 400-metre race around the running track, the distance you have travelled is 400 metres. Your displacement is 0 metres because the start and the finish are at the same point. You run 200 metres in one direction and then 200 metres in the opposite direction, therefore cancelling out and giving a total displacement of 0 metres. Speed and velocity. Speed does not involve direction. Speed is a scalar quantity. The speed at which a person can walk, run or cycle depends on many factors, including age, terrain, fitness and distance travelled. The approximate walking speed for a person is 1.5 metres per second. The approximate running speed for a person is 3 metres per second. And the approximate cycling speed is 6 metres per second. The speed of sound in air is 330 metres per second. The velocity of an object is its speed in a given direction. Therefore, velocity is a vector quantity. An example speed, distance, time question. Speed equals distance divided by time. Be aware to make sure your units are consistent. For example, if distance is measured in kilometres and time in hours, your speed units will be kilometres per hour. Travelling to work by bus takes 30 minutes. The total distance covered during this time is 9.6 kilometres. Calculate the average speed of the bus in kilometres per hour. Firstly, our time is given in minutes, so we convert into hours. 1 hour is 60 minutes. To convert minutes to hours, you divide by 60. Therefore, 30 divided by 60 is 0.5, half an hour. Speed equals distance divided by time, so speed equals 9.6 kilometres divided by 0.5 hours, giving a total speed of 19.2 kilometres per hour. Distance time and velocity time graphs. In a distance time graph, if you have a curved graph upwards, it shows the acceleration. A sloped gradient, or a straight line gradient, shows a constant speed. The steeper the gradient shows a faster speed. A horizontal line means that the object has stopped. A constant line with a decreasing or negative gradient shows that the object is travelling back to the start point at a constant speed. A curved downwards line shows that there is a deceleration or slowing down back to the start. If you are asked to calculate an acceleration at a point on a distance time graph, for example 3 seconds, you find 3 seconds on your graph and you draw a tangent to the curve. A tangent is a straight line that touches a curve where the areas either side of your point are approximately equal. To find the gradient of your straight line tangent, divide the change in distance by the change in time. In a velocity time graph, a straight line with an upward sloping gradient shows the acceleration. A steeper gradient shows a quicker acceleration. a constant horizontal line shows an object travelling at a constant velocity. A downward sloping gradient shows a constant deceleration. Total area under the graph represents total displacement. You may be asked to find the total distance travelled from a velocity time graph. Split your graph into regular shapes and find the total area underneath your graph. To calculate the acceleration at any point in a velocity time graph, find the gradient of the line. Acceleration. Acceleration's units are meters per second squared and can be calculated by dividing the change in velocity in meters per second by the time taken in seconds. We can also use the Suvat equation. The final velocity squared minus the initial velocity squared equals 2 times acceleration times displacement. A reminder that displacement is distance but in a given direction. Therefore, in exam questions involving displacement, the word distance may be used. An example question: a train travelling at 32 meters per second slows down to 18 meters per second over a distance of 365 meters. Calculate the deceleration of the train over this distance. Here, we do not know the time taken, so we cannot use the first equation. We use the Suvat equation. The final velocity is 18 meters per second. So we do 18 squared minus 32 squared equals 2 times the acceleration times 365, giving us minus 700 equals 730 multiplied by the acceleration. Divide the 730 to give you acceleration equals minus 700 divided by 730, giving a negative acceleration or deceleration of minus 0.96 meters per second squared. To note at this stage, if an object is falling under gravity, it will have an acceleration of approximately 9.8 meters per second squared. Newton's laws. In Newton's first law, we look at the resultant force. If the resultant force acting on an object is 0, the object is either stationary or moving at a constant speed in the same direction, so the object continues to move at the same velocity. When a vehicle travels at a steady speed, the resistive forces balance the driving force, giving a resultant force of 0 newtons. Terminal velocity. There are 3 stages as an object falls. At the start, the object accelerates downwards due to the force of gravity. As the object's speed increases, frictional forces such as air resistance or drag increase. At terminal velocity, the weight of the object due to gravity is balanced by the frictional forces and the resultant force is 0. This constant speed that is reached is known as the terminal velocity. Inertia, the tendency of objects to continue in their state of rest or uniform motion. Inertial mass is the measure of an object's resistance to acceleration when a force is applied. Newton's second law. The acceleration of an object is proportional to the resultant force acting on the object and inversely proportional to the mass of the object. Given by the equation, force equals mass times acceleration. This equation is not on the physics equation sheet and therefore needs to be learnt. An example question. A 1,450 kilogram car accelerates uniformly from rest. It reaches 24 meters per second in 9.2 seconds. Calculate the force needed to cause this acceleration. First, we must calculate the acceleration using change in velocity over time. The change in velocity is 24 minus 0, as the car was at rest, divided by 9.2, giving an acceleration of 2.6087 meters per second squared. Using force equals mass times acceleration, we do 1,450 times our acceleration of 2.6087, giving us a force to three significant figures of 3,780 newtons. Investigate the effect of varying the force on the acceleration of an object of constant mass. Required practical. We will use a trolley and a sloping runway, changing the mass of the trolley by adding masses. In changing the force applied on an object, it will in turn change the acceleration. Increase the force by increasing the masses that are carried by the object. Using the formula to calculate force, mass times gravitational field strength, which is 9.8 newtons per kilogram. Measure the acceleration of the object with light gates or ticker tape. Light gates are more accurate as minimize human error. Plot a graph of the force versus the acceleration. Acceleration is directly proportional to the force exerted on the object, so you will see a straight line graph through the origin. The hazards involved are using an electrical appliance, causing an electrical fault, ensure no wiring is exposed, the masses may fall on the floor and on the feet, causing bruising. Use relatively small masses to minimize this risk. Newton's third law states that whenever two objects interact, the forces they exert on each other are equal and opposite. This explains why, when sitting in a chair, we do not move. The downwards force of weight will be equal and opposite to the upwards force, the reaction force. Stopping distance. Stopping distance is the sum of the thinking distance plus braking distance. Thinking distance is the distance the vehicle travels during the driver's reaction time, from when spotting a hazard to just before pressing the brake. The braking distance is the distance the vehicle travels under the braking force. So as soon as you hit the brake and come to a stop, that is the braking distance. For a given braking force, the greater the speed of the vehicle gives you a greater stopping distance. The distance for a vehicle to make an emergency stop varies over a range of speeds typical for that vehicle. Investigating reaction time. Reaction times vary from person to person, ranging from 0.2 seconds to 0.9 seconds. A driver's reaction time can be affected by tiredness, drugs, alcohol, and distraction. We can measure a human's reaction time using a ruler drop experiment, where in partners, Student A holds a ruler at 0 centimeters above the hand of Student B. Student B rests the arm on a table and catches the ruler when dropped. Use a conversion table to convert the distance caught into a reaction time. Or the use of computer programs. Using a computer program that requires a student to press a button whenever they see a light flash. The ruler drop experiment can be done anywhere, whereas using a computer program is only accessible for schools with enough computers. If testing a factor, for example, how caffeine affects reaction time, you must ensure a comparison to a student who has not had any caffeine to ensure the results are valid. Factors affecting braking distance. When a force is applied to the brakes of a vehicle, there is work done by the friction between the brakes and the wheel. This reduces the kinetic energy of the vehicle, slowing it down and causing the temperature of the brakes to increase due to the energy transfer. The braking distance of a vehicle can be affected by adverse road and weather conditions, for example, wet or icy roads, and poor conditions of the vehicle, for example, poor brakes or a lack of tread in the tyres. The greater the speed of a vehicle, the greater the braking force needed to stop the vehicle in a certain distance. The greater the braking force, the greater the deceleration of the vehicle. Large decelerations may lead to brakes overheating and loss of control. Momentum. Momentum is defined by the equation momentum equals mass times velocity. This is not given on the physics equation sheet and therefore must be learnt. Momentum's units are kilogram meters per second, mass in kilograms, and velocity in meters per second. If an object is not moving and therefore has a velocity of 0 meters per second, the object will have no momentum. In a closed system, the total momentum before an event, like a collision, is equal to the total momentum after that event. This is called the conservation of momentum. Conservation of momentum. Before and after a collision of cars. Before a collision, a car has a mass of 1500 kilograms and is travelling with a velocity of 8 meters per second. The second car is stationary. Its velocity is 0 meters per second and has a mass of 900 kilograms. Calculate the total velocity that the cars are moving after the collision. Because the total momentum before and after the collision are equal, we calculate the total momentum before. Momentum equals mass times velocity. The momentum of car 1 is 1500 multiplied by 8, plus the momentum of car 2, which is 900 multiplied by 0. This equals a total momentum before the collision of 12,000 kilogram meters per second. Therefore, the total momentum after the collision is 12,000 kilogram meters per second. To calculate the velocity, we rearrange the momentum equation, giving velocity equals momentum divided by mass. We find the total mass of the two cars, 1500 plus 900. And we do 12,000 divided by this total mass, giving a velocity of 5 meters per second. Changes in momentum. Combining the following equations, force equals mass times acceleration and acceleration equals change in velocity over time, can give the total equation of force equals change in momentum, which is mass times the change in velocity, divided by the change in time. This calculation can be used to calculate impact force in a collision. Since 1965, all cars manufactured for use in the UK must have seat belts. It is safer for a car driver to be wearing a seatbelt compared with not wearing a seatbelt. Explain why. The seatbelt stretches and the driver takes a longer time to slow down and stop. This gives a larger value for our denominator in the force equals change in momentum over time. A larger denominator will give a smaller value for the force. The change in momentum for both drivers with or without seatbelt will be the same. So a much smaller deceleration. Therefore, a smaller force is exerted. so the driver is less likely to have an injury when wearing a seatbelt. The same principle is applied when we use airbags or protective clothing in football or American football matches.